Okay, welcome to the class, and we are going to discuss something completely new today. We have seen it in CRC, we have seen, okay, but for PDCCH chain, and we'll see how it is used for PDCCH chain, and basically this is something new. This is something very specific to PDCCH chain, okay, and that's what we are going to discuss. We'll start discussing this PDCCH chain, okay, and before we get into understanding the complete PDCCH chain, so let's recap what we are essentially doing here, okay. What is the input which we want to encode at the physical layer? This is the DCI, okay, and we saw that in great detail yesterday, what can it contain, okay, and we looked at some of the parameters, some of the fields of this DCI, we discussed them in great detail, okay. Two things which we discussed was like scheduling in time and scheduling in frequency, okay. And then of course there are a lot of other fields in this DCI, which some of them which we are very comfortable with. One is MCS, right, okay, 5 bits for that, okay. Then whether the DCI can be used for downlink scheduling or as an uplink grant, okay. Recall that base station makes all the decision, and it is the DCI which is used for both these purposes. First one is downlink scheduling, other one is uplink grant, okay. So let's say the content of DCI is decided, okay, which needs to be transmitted, okay, and again this is raw information, you cannot simply send it over here. I mean, it has to undergo certain processing, and the ideas remain same as PDCCH processing, okay. First thing you immediately see is basically CRC. As soon as you get DCI, as soon as physical layer gets DCI from the MAC layer, then the CRC gets appended. Again it is 24-bit CRC, okay, right. The first thing you see here is something different, which is CRC scrambling, and that's what we are going to focus on, okay. Why is it done, and why is it not done in PDCCH, why is it done in PDCCH, okay. We are going to spend today's lecture on understanding this, okay. Then there are other aspects which are different, okay. You will immediately see there is this polar coding instead of LDPC coding, okay, right. And then there is something called CRC interleaver, which is again different from, which is not there in PDCCH chain, okay, which is there in PDCCH chain. We'll understand this also, okay. We'll understand this also, why this is there instead of LDPC. We'll understand subblock interleaver also, okay. After that you see this is more or less same as what we have seen in PDCCH chain, okay. There are subtle differences, that it is 4-QAM modulation. PDCCH you use only 4-QAM modulation because it is robust to noise, okay. And then reverse processing, okay, 4-QAM demodulation, again de-scrambler, rate recovery. So you do the opposite of what you are doing in the transmitter. Subblock de-interleaver, polar decoding, CRC de-interleaver, CRC de-scrambling, CRC validation, okay. We are going to understand each one of that. I am showing you this, the different blocks in this chain, okay. So let's start with the first block, okay. We'll keep coming back to this chain, we'll keep referring to it, okay, till we finish it, okay. But we are going to spend a lot of time understanding the complete architecture of PDCCH chain. It's very important because that's the first thing user does for data decoding, okay, and you'll see how interesting it, and that affects the design of this chain. And whole of this, okay, in whole of this chain, polar decoding is the most complicated block, okay. And then all these designs are basically, all these blocks are designed around polar coding, so that this polar decoding complexity can be reduced, and we'll see that. So first thing is, why polar instead of LDPC? We saw that the payload, DCI payload is very small, okay. In fact, I'll give you the number. In downlink, for downlink DCI, it is only maximum 140 bits, okay, right. So it was shown that polar coding works better for these smaller block lengths, okay? That's why it is there, okay. Other non-technical reason is that one company had a patent on it and they were able to push it, okay. Then it basically, polar decoding has low power and hardware consumption, and you'll see that a user will have to repeatedly do this polar decoding, okay. Hang on to it, I'll tell you why, okay. And so this is because it is on the user side, okay. So user, if the first thing it does, and if it doesn't do it efficiently, then you are going to run out of battery, okay. So these are the key features. Okay, first is like this low block error for short block lengths, and then it requires much lower hardware consumption than the LDPC decoder. Okay, and low power is also there, another aspect. So what are we going to look at? We are going to look at this CRC and then why this CRC scrambling is done. Okay, so what is this? So let's say that DCI has come, okay, and that the DCI is denoted as A0 to A minus 1, okay, capital A bits. L in CRC, that is denoted as P0 to, it should be PL minus 1, that's a typo, I'll correct it, I do not notice, okay. So this L in CRC has been calculated, okay. We know how to do that. We have seen it in the PDCCH chain, okay. The ideas of algorithm remain same, okay. So this is the L in CRC which is calculated. Now the bits after CRC attachment are denoted as this, B0 to B minus capital P minus 1, and what is B? B is A plus L, okay. A is the length of DCI and L is the CRC length, okay, right. And what is A? Length of DCI. And now what is the relationship between AK and BK? Okay, so this is the input DCI and this is the data after attaching the CRC. Okay, I'm just going through how standard denotes it. Okay, what is BK? For the first A bits will be without CRC. Okay, right. This is a payload, and then the CRC gets appended. Correct? You read this. So this is the output of CRC attachment block. Okay, what are we saying? First AK bit come as such. This is the payload, and after that you see this from A to A plus L minus 1, that's the CRC length. Okay, what will happen? This is, you run this index, so what will be Ath bit? What will be that? It will be the first CRC bit. Okay, and then it will go up to A plus L minus 1. What are we saying here? AK is the input to the CRC block and BK is the output of the CRC block, and this is the length. Okay, and this is the output. Fine. So A is the input, B is the output. Okay, right? Done. So what we have at this stage is the CRC attached DCI. Okay, and what I showed you after that was what was that block? CRC Scrambler. Correct? Okay. Now, why this scrambling is done, I'll come little later. I'll first tell you how it is done. Okay. The need of doing it will, I'll tell you in another 10 minutes. Okay. So what is done here is that the CRC which is calculated, this 24-bit CRC, is scrambled with a 16-bit RNTI. I introduced this to you. Okay. So what is this? Radio network temporary identifier, which is an identity given to the user by the network, right? And this is a 16-bit identifier. Okay. Now what are we saying here? Okay, this is basically this 16-bit. It's, you are not generating any other sequence. You take this RNTI, okay, and that becomes your C of n. Okay, you are not generating any other sequence. You take this RNTI, convert it into binary, and that's what is your 16-bit RNTI. Okay, that's what you are going to scramble it with. So what is this? You are denoting this RNTI something like this. That's how standard does it, the standard notation. Okay, so what is X RNTI 0? This is the MSB of the RNTI, and this is the LSB of the RNTI. Okay, right? So binary. Okay, fine. So what is happening here? What will happen here is, so the output of this RNTI scrambler, it is denoted as C. Okay, right? C0 to CK minus 1. K is A plus, did we denote K? This is B, okay? Yeah, it should be B, okay? Why it should be B? Because what are we doing, okay? We are just taking in this, you look at this output, what are we doing here? Output of RNTI scrambler, okay? What is this output? You look at this, that's what it will tell you what this should be, okay? What is this? CK is equal to BK. BK is the input, okay? CK is the output. And what is happening here from K is equal to 0 to NDCI plus 7, okay? Right? What are you doing here? They come as such. And the last 16-bit, you are basically scrambling with the RNTI. That's what it is. Can you see this? Okay? What is this? 0 to NDCI plus 7. NDCI is the length of the DCI. Right, plus 24-bit we are appending, okay, that's the CRC. So first 8 bits of the CRC remain as such. The last 8 bit of the CRC, we are scrambling with this RNTI. And how are we scrambling? This is this BK, right? Where is this index K running from? NDCI plus 8 to NDCI plus 24, right? So the last 16 bit we are scrambling, that's what it is, okay, right? And if you feed in over here, where is this K running from? K will run from NDCI plus 8. So what happens, okay, right? This is NDCI, okay, correct, plus 8, and then so X RNTI will become 0, correct, and what will come here over here is NDCI plus 8. Right, okay, from 0 to NDCI plus 7, you don't scramble, and the last 16 bit you are scrambling, correct, and you are subtracting this so that it becomes XRNTI 0, 1, 2, 15. Is this clear? What are we doing here? We are taking the bit stream and scrambling the last 16 bit because the last 24 bits are CRC, and out of 24 bit, we are scrambling only with scrambling the last 16 bits. Fine, okay, so this should be B, okay, right, because input should be same as the output, the length of the input should be same as the output, okay, fine. So what happens at the receiver? What will the receiver do? Receiver will unscramble and then validate the CRC, okay, right. What will it have to unscramble with? It will have to unscramble these 16 bits, correct, okay, and for that, of course, it should know the RNTI, okay, right. So it is assumed that the user has already found out the RNTI, okay. Now, so at the receiver, what happens? BK becomes this first, this NDCI plus 7 bits will go as such. Then what happens here? You take this CK and then you again scramble it with this sequence, right? And what is CK? This is a sequence, okay? So you just substitute it over here. What is happening? XRNT, you again scrambling with the same sequence, okay? There's a bit stream of zeros, and what you get back is BK. Right? Okay, normal scrambling ideas, but how is it different from what we have usually done is basically we are scrambling the CRC, and we are scrambling only the 16 out of 24 bits bit CRC, we are scrambling only 16 bit because RNTI is defined to be 16 bits. Fine, okay. So that is the completion of CRC scrambling block, okay. That's how it has to be done. Now the crucial part is why it has to be done, right? Okay. That's where we'll understand how this, like the overall philosophy behind like this control chain, okay. What happens when a user is trying to get data from the base station, okay. So let's see that. So this is BK, okay. So need for CRC scrambling, okay. We saw this yesterday, okay, that DCI, how is DCI transmitted? The DCI is transmitted in some slot, okay, and after reading this DCI, only user can find out whether its data is scheduled or not. Please understand this. I am making a very careful statement, okay, right? That user has to find out whether a DCI for this user has been scheduled or not, okay, right? User doesn't know in advance unless and until it has some like earlier DCI, okay. Let's say it doesn't have, it started from state 0, okay. Initial t is equal to 0, okay, doesn't have any other DCI, any other previous DCI, okay. So what will happen is it will wait for this DCI, okay, right, and how is it going to find out whether its DCI is coming or not, okay, right. There is a concept called blind decoding, okay. User doesn't know in advance whether its DCI is going to come or not, okay. User has to figure it out, okay. And how does it figure it out? That's what is blind decoding. Because the user doesn't know its DCI is coming or not, so it is blind. Okay? Unless and until it figures out that its DCI is there, okay, it cannot decode the data. Okay? It doesn't even know whether its data is scheduled or not. Okay? Right? Now, so we have to learn about how this DCI is transmitted. Okay? A brief summary is, okay, user will have to search for the DCI, okay, and how will it search? It knows as RNTI, right, okay. So what will happen here is, okay, I'll have to go back too much. So what happens? Polar decoding, okay, I'll decode the data at the receiver side, okay, U is going to decode the data, then it'll unscramble this CRC with this RNTI, okay, because this scrambling is user specific. It's how this RNTI is different for each user. Okay, so if it is scrambled with some other user's RNTI, it will give you wrong data. User will not be able to validate it. Fine. Now, so what is happening? That this is not its DCI. And you'll have to search for other DCI. Correct? Then you'll have to do the same process again. Correct? Okay, so it has to make multiple such attempts. User has to make multiple such attempts to find out whether its DCI is there in this slot or not. Okay? And I'll tell you how many maximum such attempts can be made in the standard. Okay, we'll discuss all that, but you understand what is happening. A broad picture, okay, user is not aware whether its DCI is coming or not, correct? Okay, user is aware only of its RNTI. Now if the base station wants to schedule this user's data in this slot or any other slot later, okay, it'll take its DCI, scramble it with this RNTI. Then after that, it's the user job to figure out whether its DCI has been scheduled by running the complete receiver chain and finally unscrambling it using its RNTI. If it is its own DCI, then things will be fine. Okay, then the CRC will get validated. Then it will be able to, then it will know where its data is scheduled. Okay, so you understand the blind part? It is searching. I'll explain that in detail how it searches, okay, but it has to search. And that search is blind. So your mobile every time does that. Okay, right? Every 0.5 millisecond in 5G, it does the search unless and until it has been put into a sleep mode by the network. Okay, right? So you understand the complexity of this. It has to make multiple attempts. So the receiver chain, this PDCCH receiver chain has to run multiple times. So it has to be designed such that it consumes low power. Otherwise, every half an hour your mobile will run out of battery. It's not a nice thing to happen. Okay, so the standard has to be designed appropriately. Okay, understand this? Okay, this is a broader picture, and let's see. So what happens? What am I saying here? How this DCI is transmitted. Okay, so this DCI is transmitted on certain set of resources. Okay, those resources are called control resource set. And what are the resources? Time frequency resources, PRBs. Okay, they are given slightly different name here for PDCCH. That's what we are going to study. Okay, how these core set, okay, they are called core set, okay, control resource set, and how they are designed. They are designed to facilitate this blind decoding. Okay, right? Let's see that. So what is this core set? Basic definition: time frequency resource where DCI may be transmitted for a user. Okay, right? They are defined like this. Okay, I'm giving you few examples, okay, of core set. Okay, how they are like technically defined, how they are like how it is done, where are the formulas for defining this? That will come later. Okay, what are we saying here? These are the predefined core sets. Okay, where these DCIs can come. Okay, typically you will see that these core sets are there in the first few symbols because that's where the control information has to come. Right? Okay, so most of them are there. And what is this core set for? This is meant for URLC data. Right? If some data comes in between, okay, URLC data, high priority data, so immediately this core set will be scheduled. Fine. So what are they? You see this, they are time frequency resources on which these DCIs can be scheduled. Okay. Right? User will broadly have these knowledge of these core sets. Right? So now what happens? Let's read about this core set. The core set can occur at any position within a slot and anywhere in the bandwidth. Bandwidth 275 PRBs, anywhere in the slot 14 symbols. Right? Okay. Now if you do not put any restriction on these designing of this core set, they are 275 PRBs. Right? How is the user going to search? He'll keep searching all the time. He'll never be able to decode data. Okay, so certain restrictions are imposed on these core set so that it becomes easier for the user to search for the DCI. Okay, get it? Okay, so for common traffic scenarios, when a scheduling decision is taken once per slot, okay, they are scheduled in the beginning. Okay, core set is located at the beginning of the slot because it makes sense. If the data is scheduled here, right, first the DCI has to be decoded by the user. Okay, so typically they come in the beginning. Can be transmitted at other instances also. Just for example, URLC. Okay, URLC transmission occupying only a few of DM symbol without waiting for start of the next slot. What am I saying? URLC typically like lesser amount of data. Okay, so it can be scheduled in the middle also. okay, but key concern is the latency. Okay. So if the data comes, typically lesser amount of data than EMBB applications. Okay. So it will not require multiple slots. It can be accommodated in few symbols here itself, but it has to be scheduled immediately. That's where this core set can come, okay, for URLLC. Okay. Now, what is the technical term? UE has to monitor these core sets. Okay, it has to keep checking for these. It has to keep checking these core sets whether DCI is coming or not. Okay, and blindly decode its DCI. I gave you a brief idea of how this blind decoding is done. Okay, right? Now the core sets are designed such that user will require a maximum of X blind decoding attempts to find out whether its DCI is transmitted or not. That's how these core sets are designed. Okay, that UE should within these maximum number of attempts, it should be able to figure out whether its DCI is there or not. If it's not there, it will raise its hand after making these maximum these attempts. Okay, and what are these attempts? For 30 kilohertz subcarrier spacing, maximum of 30 attempts are allowed. Okay, that's how they are designed. Okay, within 36 attempts, it will be able to figure out. Okay, so you see this every 0.5 millisecond, 5G phone is running this chain. Hopefully maximum number of 36 times, correct? Okay, right? For 120 subcarriers, 20 attempts are allowed. Millimeter wave, okay, so certain more restrictions are imposed, so maximum number is 20. Fine, okay, not like data. See, the philosophy is different now. You don't do all this for data. No such blind decoding attempts. You have to run your LDPC, the complete receiver chain only once, okay, because you know where your data is coming. But here you don't know whether the DCI is coming or not. After 36 attempt also, right, user data may not be scheduled, so it might not get its DCI, it's fine. Okay, right, so that's what it is. Okay. So that changes the complete design philosophy of the PDCCH chain, and we'll see that. Okay, I'll convey these key ideas to you. Okay, and DCIs are transmitted on specially designed control resource set. That's what we have said. It's there for the record. This is okay. Coming again. Okay, the picture. So base station does not explicitly indicate the user identity for which DCI is meant. It is not telling the user, any user, whether its DCI will be scheduled or not. Okay, it doesn't tell that. And the way it is told is basically by scrambling. And user has to do these blind decoding attempts. That's what I'm saying. It's not explicitly indicated to the user. Okay, only way the communication can happen is through this like scrambling. Okay, indicated by scrambling last 16 bits of CRC with RNTI. User has to make multiple blind decoding attempts to find out its DCI. Okay, right? And that's the idea. And that's what we are going to see. PDCCH chain is designed to reduce the pain of blind decoding. Okay, right? It's an extra overhead, correct? Processing overhead. And if you don't do it smartly, as I said, okay, your battery will be dead in no time, right? It's okay if it is like hardware is fine. Okay, you have designed it somehow, you have designed it, but if standard does it badly, that's the standard design part. Okay, if standard is designed poorly, then this blind decoding can be a massive failure. Okay? If it takes hundreds of attempts to find out whether this DCI is scheduled or not, then of course nobody is going to buy 5G phone. That's the first stumbling block, correct? Okay, so that's what I am saying. I'll bring it back to you. That what are we doing here? The same chain. Okay, I brought it back just to tell you that all these modules, CRC interleaver, that's the first thing we'll see. Okay, the CRC interleaver, how is it designed? So that it can do something called early termination of polar decoding. Okay, it doesn't even decode the DCI completely. Okay, that's how the CRC interleaver is designed. That we are going to see that. Okay, right? And then first, like as we did for LDPC, okay, I'll give you some key aspects of polar decoding. How is it designed? Okay, so that it helps us in understanding the overall transmitter and receiver chain. Okay, then we'll spend one class understanding the CRC interleaver. How is it designed to reduce the pain of this blind decoding? Okay, right? And then after that, these blocks will come and they are more or less similar to the PDCCH chain. Okay, so I'll stop here and we'll continue in the next class where we'll discuss this polar encoder. Okay, thank you.